So the Rosenberg Forum falls under the Ag and Natural Resources Division of the University of California system, and Glenda Humiston, who's the Vice President of the University of California in charge of Ag and Natural Resources, is with us, and we'll have a few words before we get to the program. Glenda?
Thank you, Sarush. I appreciate that. And welcome to everybody that's joined us this morning. These webinars are our way to keep the conversation going around water policy this last few years when we've been unable to get together and face-to-face. We're looking forward to doing that at some point in the not too distant future. I'm really excited about today's topic because hydropower is a huge issue on so many levels. We've got some really excellent speakers this morning looking about the impact of hydropower on carbon emissions and our river ecosystems. This is part of our ongoing mission to facilitate discussions around water policy internationally. So without further ado, I'm going to turn it back to Sarush to kick off our speakers and get us going this morning. And once again, thank you all for joining us. I hope you really enjoy the topic and the discussion, and I look forward to a lively discussion after we hear from the speakers.
Thank you, Glenda. And at this point, I will turn the meeting to my colleague Yun Duan, who is going to essentially chair the first part with our four talks. And after that, we go to a Q&A, and Christina Babbitt, my colleague, will be leading that effort. And we also like to introduce you to the advisory committee of the Rosenberg Forum. A good number of them are already online and participating in today's meeting, but because we lost some time, we will not go through individual introductions. The pictures are shown here for you, and we will move to the program. So please, for people who do have questions, they can enter it into the chat box. And depending on time, at the end, we may have some one-to-one interaction as well. So with that, Yoon, are you ready?
Yes, I am. Yes, thank you. Thank you, Sarush. Welcome, everyone. Good morning, good evening, good afternoon, whatever you are. And so welcome to the Rosenberg Forum webinar on impact of hydropower on carbon emissions and river ecosystem protection. As everyone knows that climate change is a global emergency that goes beyond national border. To tackle this emergency, a nation comes together in Paris in 2015, reached the agreement to try to control global temperature rise to be within 1.5 degrees from the pre-industrial level. To achieve this, a drastic reduction in carbon emission is a must. So in this context, hydropower play an essential role in this. And but hydropower is not without controversy. So today we have four distinguished speakers to talk about different aspects of hydropower, particularly its impact on carbon emissions. So we have four speakers, and each of them have 20 minutes. The first speaker is Dr. Samuel Bolkenhau. He is the program director of Hydropower initiative of the U.S. Department of Energy. He is going to probably talk more about this program, and his title is "The Role of Hydropower in a Decarbonized Power System." Sam, please take over. You have 20 minutes. Thank you.
Great. Thank you, Duan. Welcome everyone, and thanks for the chance to speak. Thanks to Sarush for the invitation. And as you all said, I'll talk a little bit today about the role of hydropower in a decarbonized power system. As we all know, hydropower is a clean source of electricity generation, but it's also provides values related to flexible operation and energy storage that can be really critical for integrating other types of variable renewables like wind and solar to help in that power system decarbonization. So I'm from the U.S. Department of Energy, the Water Power Technologies Office. DOE is our energy ministry in the U.S., and so we focus on research and development, at least in the work that I'll talk about today. And there's a lot of interesting work across technologies that we're doing, even beyond hydropower, and even more with recent congressional legislation that has expanded our mandate quite a bit. So there's a lot going on at DOE today. I'll give a little bit of context about how we see the challenges and opportunities related to hydropower today, and then I'll also give a sampling of some of the projects that we have that may be able to spur further discussion later on. Next slide, please. So first, setting the stage on U.S. decarbonization goals. We've got goals related in 2030. We've got even more expansive goals of completely decarbonizing the power system in 2035 and the entire economy in 2050. And so the point to make here is these are really ambitious goals. Some of the technologies that I think we'll need to get to these goals don't even exist yet today. There's things like direct air capture and hydrogen at large scale. And so, some of these really need a lot more research and development. And I think hydropower, though, has an important role to play because it's a technology that exists. It is clean, it is flexible, and it is provides a lot of storage. And so there's potentially a significant role for hydropower in getting to these goals. And that technology exists today and is deployed around the world. Next slide. A little bit of context, I think, as everyone on the webinar knows, the power system's changing really rapidly. I'm just highlighting a California example. One day in 2019, the blue curve in the upper trace or in the upper graph is showing solar generation, and as you see in the middle of the day, it's quite substantial. And when you look at net demand in the lower graph, you see the familiar duck curve shape that you're depressing net load in the middle of the day, and so that means that you need to shift energy around to ensure reliability as that's happening, and you also need to ramp in some cases pretty sharply to be able to meet that net load. Next slide. I think the importance for hydropower is that it has an important role to play in as the system's changing so rapidly. So an example is pump storage hydropower, where we're seeing operations changing really rapidly due to more variable renewable energy. The graph is showing the Helms pump storage plant in California shifting over years from pumping primarily at night to pumping multiple times during the day as well. So, and that's to basically balance that variability in the solar that you have coming on in the middle of the day much more, in much greater amounts. And so between 2013 and 2015, 2016, you saw a really huge shift that corresponds to that dip in the duck curve on the previous slide. So I think this speaks to the ability of pump storage to enable additional variable renewables to come online to really support this, this expanded deployment of variable renewables. Next slide. And we see similar operational changes worldwide. So this isn't just a US thing. I'm showing an example from Japan, the Omaragawa pump storage power station. You're seeing really the same thing. You're seeing start-stops, a similar measure of pump storage operation is changing, the numbers changing quite a bit, even in a short span of years, which directly maps to the amount of increased solar that's coming online, shown in the lower graph. This is in Kyushu, one of the islands in Japan that has a lot of solar coming online. Next slide. There are also new market structures that we're seeing that encourage hydropower flexibility in the US. So the Western Energy Imbalance Market is an example. What I'm showing in this graph is just a plant's generation over one day. And you see that it's not a flat line. I mean, it's changing quite a bit. It's really moving on even 5 minutes or 15-minute increments. And this is these market structures are driven in part by the growth of variable renewables and the need to really change operation quickly. And so hydropower is taking advantage of these opportunities. And there are also challenges too related to if you're moving so quickly, if you're changing your generation so quickly, you may be increasing wear and tear, and that's something that owners and operators are seeing too. But really, this is driven, in part at least by the renewable generation that's coming online. Next slide. And a final role to highlight, I think, is hydropower can play a critical role during extreme events. So during heat waves, for example, in a couple of years ago, there were instances where, as demand increased and wind generation decreased, hydropower has quite a bit of storage in its reservoirs, at least large hydropower. And you see examples in the blue trace here of hydropower ramping up to meet that increased demand. And that's something that can really help to prevent major blackouts or other types of disruptions. And so I think there's an important resilience role that we see from hydropower in different situations. Next slide. And then stepping back a little bit to think about the energy storage role. So pump storage hydropower, as people on the call may know, is it's really a battery. It's able to store excess energy the same way that batteries are. But even reservoir hydropower has a lot of the storage capability because you're storing water behind a dam. And so the International Energy Agency did a rough survey worldwide of how much storage potential there was. And from pump storage and hydropower. And you see the yellow square is batteries, including EVs. The dark blue square is pump storage worldwide. So that's quite a bit larger in terms of energy stored. And then if you count reservoir hydropower, it's enormous. It's much, much larger than either of those two. And so I think this starts, this speaks to the ability of hydropower to provide a lot of energy storage. And, it makes clear that we should think about hydropower also in terms of megawatt hours of energy stored, not just in terms of generation. Next slide. So, that's kind of how we see the landscape. I think there's a lot of capability that hydropower has. You can click through the next 4 bullets, but there are, of course, challenges. So as the energy system is changing so rapidly, there's a limited understanding of what types of grid services will be needed. So what types of flexibility, what types of storage, firm capacity is really important. And then valuing those services is always a big challenge. Who's going to pay for them and how much are they worth? Those are big sticking points and challenges across the power industry. The second, hydropower and pump storage capabilities are bounded by interaction of machines, water, institutions. There's a lot of complexity, and some of those decisions, especially the institutional decisions, were made decades ago when plants were built. And so as we're seeing plants being relicensed, there can be questions, or they may be asked to do things that weren't in their original mandate. And so the environmental balancing environmental impacts is a really critical thing. And I think we'll hear more about that from other speakers. There are also gaps in information about how to optimize hydropower and pump storage and in planning and coordination with other resources. So lithium-ion batteries are really well suited to provide some types of storage, but there are other types, especially longer durations, that pump storage, at least currently, may be better suited for. And finally, on the technology side, current hydropower and pump storage technology may not always be designed for flexible operation. So if you're asking for many more starts and stops per day from a plant, or if you're asking for a ramp rate that moves up sharply to balance the solar coming offline in California, the technology may need improvements and enhancements as well. Next slide. And so there are a lot of opportunities too that we see there, and that's the reason that we have this work at DOE that's focused on this issue. So the HydroWires initiative, the initiative that I lead, is focused on understanding, enabling, and improving hydropower's contributions to reliability, resilience, and integration. So really supporting this decarbonizing role of hydropower. Next slide. We've got a number of research areas and different projects from the DOE national laboratories and from industry, from academics, including Sarush and his team in this initiative. And so some of the broad areas they're organized under: value under evolving system conditions, quantifying the value of pump storage, understanding market and policy implications, capabilities and constraints, so improving capabilities to model hydropower, which is really a challenge due to those, those conflicting constraints that we just discussed. Quantifying operational trade-offs as well, which I think we'll touch on today. Operations and planning, thinking about how to increase flexibility through operational strategies, and technology innovation, increasing the flexible capabilities by developing new technologies, hydropower hybrids, new types of pump storage. That's all within the type of work that we try to do. Next slide. So one interesting project, I think, for this topic of the role in decarbonization is, basically spurred by this question of, okay, hydropower can enable more megawatts of variable renewables because it's flexible. That's something we say it's easy to talk about, but really at DOE we want to be quantitative and try to be, as rigorous as we can with these, with these types of statements. And so this is a hard question. There's no easy, straightforward conversion that you can do because it depends on the entire power system. It depends where the plant would be located if you built a new pump storage plant, for example. And so there's a lot of complexity there, but there is some work to try to get a rough cut at it that we're working on. Basically, if you take out a certain amount of fossil fuel generation from the power system and replace it with storage of different durations, which could include pump storage and solar and wind, what is that ratio? So how much storage and how much variable renewables would you need to ensure reliability? And so we look at a balancing area level across the US. Next slide. And so some of the rough results that we find, there's a lot of caveats here, but if you do that type of substitution, you find that storage can enable around 1 to 2 megawatts of wind and solar per megawatt of storage. And 10-hour storage, such as you may get from pump storage, is much more effective at enabling wind and solar deployment relative to 2-hour storage, which would be a shorter duration lithium-ion battery. So this is the type of work that we're trying to do. Sometimes, even with complicated questions, we need policy rough cut estimates that we try to understand and communicate. Next slide. Another project that we're working on is dealing directly with this idea of trade-offs between environmental performance and flexibility and flexible operation of hydropower. So if you're ramping or doing other types of flexible operation, you can certainly affect downstream ecosystems. You can have other impacts on the environment that may is something that in a licensing proceeding you would need to consider. And so we're doing some work on looking at how would the different types of services that you may provide, shown on the left, be affected by different types of flow requirements in license that exist today. Sometimes in the red it's highly affected, or it could be constrained by those flow requirements, and then others in green or yellow, it should be less affected. And ultimately what we're trying to find with this is, are there win-wins? Are there examples where you could increase flexibility through some operational change or even technology, and also improve habitat downstream for salmon nests or for bottomlands habitat or whatever it might be? So there's a possibility there for win-wins, even though it is very complicated and you do need to look at the full picture. Next slide. We've also got some work on pump storage hydropower, and I'll speed up a little bit to make sure I don't go over. But for pump storage hydropower, one of the things that we hear sometimes, kind of a myth that we see circulate, is that to build new pump storage, there are no sites available, or it's too hard to find the right site. And there are a lot of constraints on where you could build new pump storage in the US. But what we've done is a resource assessment, and we found that there are quite a large number, 15,000, if you just look at the geography and where it might be possible, and excluding national parks and lands that would otherwise not be suitable. So that's not to say that anyone would ever develop all of these sites, but it is something that can be considered, and that we're looking at working with developers to make this more accurate, and then understanding what type of research questions this would spur for us. There's also some innovative pump storage hydropower work that we're funding on completely new technologies that could avoid some of the challenges of deploying conventional pump storage. So is there a way to reduce the footprint of a plant by digging the basically making the turbine underground without a powerhouse, and digging straight down and avoiding having to excavate a large part of the mountainside to do it, to save on cost and reduce the impact. Next slide. We've also got some other work, just kind of teasers here on hydropower hybrids demonstration. We've demonstrated, working with Idaho National Lab and other national labs, a way to add a battery to run-of-river hydropower plants to increase their flexibility and allow them to do black start. So if the power system were to completely turn off, then adding a battery to these hydropower plants lets them basically reboot the power system, which is something that they wouldn't be able to do without that type of hybridization. There are further out white papers that we're working on related to long duration energy storage compensation mechanisms. So how can you assure financial return on investment if you're going to build a new pump storage plant, for example? And on zero carbon market designs related and what their impact might be on hydropower. So as we've got these this increasingly renewable system, the entire structure of the market may need to change or will need to change as the penetration gets really high. And so, what does that mean, and what would the impact be for hydropower? And I think the upshot is that there could be a lot of opportunity as a flexible resource with inertia that is still able to remain on the grid. Next slide. And finally, international collaboration on hydropower. I would note that, we're not building much new large-scale hydropower, not any large-scale new hydropower in the US right now, because a lot of it has been built in the past. But there are some new smaller scale projects and a lot of projects in the pipeline for pump storage. So we're really looking to international partners for increased learning. There's been countries around the world who have figured out how to build pump storage in recent years and been really successful with that. So I serve as the chair of the IEA Hydropower Technology Collaboration Program, which includes a lot of different work across hydropower. This is an old bullet list. I would note that there are new annexes, new tasks that are led by China on basin scale utilization of hydropower, and by Japan on climate resilience. And there's some other work that we're doing. We have a bilateral collaboration with Norway on a lot of hydropower research in the topics that you see here. And there's a completed forum that we did a couple of years ago on pump storage hydropower, how to get it built around the world. So I'd say that the international learnings and collaboration are really important for us. Next slide. So that's it for now, and I'll close here, but I would just say that, so we are doing a lot of work. I'm happy to talk more to anyone who's interested, but I think the point is, hydropower, it's complex. There's a lot of opportunity there. There are challenges, but we do see it as a part of the climate solution, and that's why we're supporting this type of work. Thanks.
Great. Thank you for a great talk. And as we said, we are going to have a Q&A session at the end of all the presentations. And so anyone who have questions, please put your question in the chat box. And unless somebody has a quick clarifying question, otherwise we are going to move to our next speaker. So if there's not, let's move to the next speaker. Okay, our next speaker is Professor Stefan Riedelbach. He is going to talk about hydropower plants, the carbon neutral electricity generation from an engineering perspective, and talk about different technologies. And welcome, Professor Stefan Riedenbach. You have 20 minutes to make your presentation. Thank you.
Okay, thank you very much for this nice introduction. I just share my screen.
That's terrific, Professor Riedelbach. You're good to go.
Okay, thank you. So good morning, everybody, wherever you are in the world. It's really a pleasure to share some of my thoughts about hydropower plants. If you look from a electricity generation perspective for our society, we can ask ourselves, do we really need electricity? If this is wrong, then we probably would have a romantic evening, but also we have all the achievements which we had so far related to today's life, like health, communication, tools, heating, and so forth, we don't have anymore. So probably everybody agrees that our society requires electricity. And if this is true, then we simply require power plants. And those power plants could be thermal, it could be concentrated solar power as an option, or it could be hydropower. So for those thermal plants like up here, we have essentially steam turbines, and the steam must be generated somehow. It could be coal, oil, nuclear as an example, or also through those concentrated solar panels where mirrors really redirect solar radiation to a tower in this case, and there, which is it's a device to generate steam. On the other hand, hydropower really uses, let's say, potential energy differences to convert energy towards electricity. If you have those plants, we of course also need to transport from generation to consumption sites, and therefore we definitely have a need for transmission lines. So when we have those options, the real only remaining question is which of the available power plant technologies do we want to deploy? And always we can say, and it is clear, that all power plant solutions affect the environment. It's air, it's rivers, it's ocean, soil, and then it will affect plants, animals, and humans. The real question is, what are the ethical criteria for the decision? Is it, let's say, renewability, sustainability, or is it based on pure economic considerations? So that is what we have to decide. And with this presentation here comes a plea for the utilization of hydropower technology, because I'm really convinced that this technology is for renewability and sustainability as it should be. This sketch here shows, and this is a reminder basically about the overall process, shows that the sun here evaporates water from the ocean, from other surface waters, from soil, from vegetation, and so forth. So humidity moves up, eventually condensates, and with weather conditions moves over land, and there we have precipitation and so forth. So we have here a closed water cycle, and this water cycle really is driven by solar radiation or simply by the sun. The water which is moved from the ocean, say, up to hills and mountains, this is really, let's say, a increase of potential energy. So the water is lifted to higher than sea altitude, so we have potential energy. And then if it moves down back to the ocean again, we have kinetic energy. And hydropower plants really convert both either potential energy and or also kinetic energy. So what we can say is that hydropower is driven by solar power in an indirect way. And this is a truly sustainable and renewable energy source. And a possible definition of renewable energy could be that this is energy that is collected from renewable resources that are naturally replenished on a human timescale. And this is certainly true, because if the sun doesn't exist anymore, then life on Earth is, let's say, very unlikely. Here comes a couple of examples for potential energy conversion. We see here different types of hydropowers. One is a pumped storage plant, Raccoon Mountain in the United States. We see the upper reservoir here. The plant is somewhere in the hill. It's an underground, a cavern powerhouse, and this is a tailwater, which is, I believe, the Tennessee River. So this potential energy difference can be exploited and converted to electricity, and vice versa. Electricity can be converted to an energy reservoir here. Yeah, very similar is also systems are available in Austria. You have pump storage plants or just storage plants, and in this case, Canabrava in Brazil, which can be used as base and peak load. This is also true here, but we will see that those kind of plants typically are for frequency control. So this system, this overall system, is really a conversion of energy without thermal processes. And this means that we can have continuous electricity generation, kind of as a base load, but we can also have very fast power changes to support the stability of the electrical grid. And this is really a key advantage, because thermal processes, everything which is in the power plant business, which is related to thermal processes, is relatively slow. Another, let's say, truly renewable and sustainable energy resource comes from gravity, which is based on mass attraction within our planetary system. So we have the sun, the Earth is rotating around this, is moving around the sun, the moon rotates around the Earth is rotating in itself. So this is again truly renewable and sustainable, because if the sun is not existing, also mass attraction will disappear, no life is possible anymore. Gravity forces in certain parts of the world generate tidal currents, very high tide, high and low tide here is in the Bay of Fundy in Canada. So the elevation is very, very large, the elevation change of the water level of the ocean, which means that somewhere in a narrows, somewhere we have very large tidal currents. The advantage of such a conversion towards electricity is that tidal currents are very well predictable, and therefore also the electricity generation is very well predictable. We have, and this prediction is less well for wind generation and also solar generation, because if you have clouds or you have just no wind or cannot predict very well, you have always some uncertainty and very much fluctuating electricity generation. But with this topic, it's well predictable and foreseeable. An example for the conversion of tidal energy is this system, a floating trimaran. This is really a view from above. We have trimaran here and the view from below. So this device here is anchored, and it sits there at a specific location and has, in this case, 6 propellers, which are converting tidal current towards electricity. You need to have some cable towards land and so forth. That's clear. And as an example, so at our institute, we made some simulation of such a configuration, and you see a cut here through the flow field. We see here the 6 propellers here and their respective wake flow, and we can identify the interference between those propellers and also predict the performance of such a device, under, let's say, the given tidal conditions. There is other concepts which convert kinetic energy, and this is concepts that say in principle a propeller turbine simply very, very similar to wind turbines, or shrouded propellers, which could be used in rivers because of the limited height, of the limited depths of the rivers. Those are really for pure kinetic energy conversion, and those would serve essentially as base load. And when we look at tides, and this is an example of a performance prediction of a project area. In this case, it's a European Marine Energy Center. We see here the back and forward flowing tide. We can say or simulate the tidal current and then add a large turbine array. All these dark dots here are turbine arrays, turbines. And then we can, based on the tide, we can predict really the power generation of each individual turbine, and also the interaction between those turbines, and find, let's say, the overall performance of a project area. In this case, I believe there is something like 300 turbines in this turbine array. Okay, so these are the possibilities which I consider to be relevant for hydropower, and then we want to compare this to the requirements and the properties to the electrical grid. We see that the power demand is constantly changing. So the power demand is varying all the time, and we have seen this in the earlier presentation of today. But we also say that, or it's a fact that the electrical grid as such has no storage of electricity. There is only conversion. We can use batteries, but this is energy conversion. We can use hydropower pump storage plants, is energy conversion. So if you want to really have a safe and balanced electrical grid, we need prompt generation of the electricity. And this can be visualized like this. We can state that the grid frequency really is a measure for grid stability. It's like, this balance here, we have on one side consumption and on the other side generation. And don't worry about the frequency. This is for Europe. In the United States, as an example, you might have 60 hertz, but it's the same principle. So if consumption and generation is really in balance, we have probably a nominal frequency of about 50 hertz. So if the generation is too strong, so the machines that starts accelerating, and typically we have for large plants, we have synchronous generators, and so the frequency is increasing. So we have to reduce the power of the generation to come back to the normal frequency. And the same is true vice versa. If the consumption is too strong, the frequency will move to lower values than the nominal value. And this means we have to increase the generation to come back to the nominal value. And the only measure for this is really the grid frequency. So in other words, if we have to balance this all the time, we have to have a continuous power control to maintain this balance close to the nominal frequency values. And just as a remark, grid frequency may vary depending on country, but I guess this is all what you all know anyhow. The system to achieve the balance between consumption and generation consists really of 4 levels, basically up here. Yeah, it's a primary control, secondary control reserve, a tertiary control reserve, which is mostly automated. So what we see as balancing capacities can say that we need more power or less power, and this primary reserve here, which is visualized here, has to react very fast. Yeah, so we have to have, and those times may depend a little bit on the country, but it's very fast. And then the second, and this could be achieved by hydropower plants. Today, it's often thermal power plants, but also hydropower plants can play this role. And secondary reserve, this is traditionally pump storage plants. Yeah, so we follow really with pump storage plants. We follow the electricity consumption to relieve the primary reserve. And this is, see again, the time scale is relatively fast. And then if this comes to their limits, we have to have additional plans to relieve the secondary reserve and so forth. So because of the requirement of those short times, we come back again to my earlier statement that hydropower plants are ideally suited for fast control tasks because of their physical function. And this is because they have no thermal processes included and can be very well controlled. Yeah. So as a schematic of a pump storage plant, which we see here, storage, penstock, turbine or pump turbine, another pipe to the lower reservoir. We know that the power is dependent essentially on the head difference and the mass flow through the machine. We can use this energy difference to generate electricity, or we can use electricity to build up an energy reservoir again. And as I said earlier, because of balancing services, we need both in reality. And we also can state that the overall system efficiency is very high. Optimum machine efficiencies, like for a turbine as such, can be up as high as 95%. And the overall plant, it's depending then on the sizing of everything, but we can certainly have the overall plant efficiency with 85%. Typical machines are built like this. This is a very large machine. We have the turbine down here. We have a circulating water flow, which produces angular momentum of the flow. And this angular momentum is removed within the runner, and the radial inflow to the runner, axial outflow of the runner, in this case a Francis turbine. And this runner of the Francis turbine is coupled, directly coupled with a generator rotor up here. And this generator rotor produces voltage and current within the stator bars here. And those from there, the electricity is moved to the transformer. As I mentioned, that typically for those kind of systems, we have synchronous generators. So that means the rotational speed of this system is more or less directly coupled to the grid frequency. So the measure as such, which I said was a grid frequency, can be directly felt within this system. So if the frequency is dropping, we increase the power here to accelerate again this rotational masses, and vice versa. Okay. An example for very fast reaction times, which are needed for this flexibility of our electrical grid, is presented here. So this is a plant in pump storage plant in southern Germany, and a schematic about operational transition times. We have a standstill condition, and if we want to go to generating modus, we can come up to synchronous speed of all the rotational masses within 70 seconds. Then the generator is synchronized, but still has 0 megawatts. And then in another 30 seconds, we can increase the power up to the maximum power of the individual unit. In this particular case, there is 4 machine sets. So in total, this plant has like almost 1,000 megawatts. Yeah? And the same is true for the pumping operation. We can go from standstill within 1.5 seconds to a consumption of almost 250 megawatts. And this would be possible for 4 machine sets. So consuming between 1,000 megawatts roughly. Okay, and also from pump to generation, it's very short conversion times. Yeah? So
Professor Rittelbach, I'm sorry to interrupt you. I just want to do a quick time check. We're very close to time. So
okay. All right. Okay. So maybe give me four more slides here. If you look at research requirements, because of these high flexibility needed and fast operational changes, we need to look in flow simulation, which defines the loading of machines, structural dynamic, the answers related to lifetime, plant dynamics for fast operational changes, or combining all of this. Model testing and so forth. As the time is relatively short, I prefer now to jump into 2 or 3 examples. And this is an example about operational transients in turbomachinery. So we can predict the behavior under operational transients of such a plant, which is a real plant in Spain in this case here, and see what happens.
Sherry, you need to mute on your side, please.
Yeah, thank you. What happens if such a pump turbine, for example, moves from a steady state pump operation point towards a steady state turbine operation point? So we are working in our institute for those kinds of problems. And what we also possibly need, because this is very complex and challenging numerical approaches, we may want to validate this. And in our lab, again, we have such kind of laboratory facility, and this is a real view on it. It's a relatively large facility, which is able to come up with operational transient simulation in an experimental way. Yeah, and with an instrumented model turbine, we can come up and find dynamic strains and stresses within turbine equipment. Another example would be what I call predictive damage assessment. So in this case, it's a cavitation across an airfoil, and we use convolutional neural networks to predict, first of all, whether cavitation is existing in a machine or not. And then also we're working on cavitation erosion, whether those methods may give an indication about the amount of cavitation erosion. A third example is, which is also kind of a prediction, is operation point estimation on pumping, again using convolutional neural networks. And we have here a pump, simple pump, to gather a lot of data equipped with sensors, and then we see in how far we can predict the head flow curve, typical pump characteristic here, based on those signals only. Yeah, this is an example. All the gray points are kind of learning data, and then the blue and red points. Blue means predicted value, and test on the red is the real test value, the true value, ground truth, basically. Yeah. For predicting, exactly predicting the loading within a turbine, we need to have very accurate prediction of flows in the turbomachinery. And this not only for optimum condition, but also for extreme off design and possibly for operational transients. And for this, we are looking in very large flow simulation topics, which at the maximum, this simulation may have 100 million flow elements. We have a very large supercomputer at the University of Stuttgart. And so we can predict relatively accurate the loading of the machine, and then can come up with fluid structure and fluid structure interaction topics to assess the lifetime at extreme off design relative to optimum conditions, but also for operational transients. So it's basically a prediction and simulation of forced vibration. Yeah, maybe I skip this lower part and come almost, I believe, to my almost last slide here. This again shows this European Marine Energy Center. This is Scotland. This is Orkney Islands, and this is the area where there's a large number of tidal current turbines. And the same systematics, the same methods can be used for river flow prediction, because for these kind of hydrokinetic turbines, you again want to identify locations with high flow speed to get a maximum conversion of electricity. And so that means, as summary, hydropower plants have very high efficiency levels of energy conversion compared to all other power plants. They have very high flexibility and capability for fast and very fast power output changes with 1 minute or less, and excellent capability for stabilizing the electrical grids with a high share of volatile renewable energies such as wind and photovoltaics. Yeah? And of course, hydropower typically is multi-purpose plants. Okay, with this, I'd like to thank you very much for your attention, and I'm of course available for questions you might have. Thank you very much.
All right. Okay. Thank you very much, Professor Rosenberg. Yeah, two excellent talk on the hydropower, and one from a top level of research program point of view, and this is more from a technology point of view. And I'm sure people will have questions later, and we are going to have a Q&A session at the end of the talks. And so now, we are going to move to our third speaker, Dr. Chiu-Wen Chen. He is the director of River Ecosystem Research Center in Nanjing Institute of Hydraulic Research. The two talks on hydropower, this one actually is on the other aspect, is on the protection of the river ecosystem. So Dr. Chen, so it's you have 20 minutes to present your talk.
Okay, thank you, Professor Duan. I will share my screen. Okay. Yeah. So thank you very much. Good morning and good evening, depending on where you are. So I am very honored to give this talk in the forum. In the last two speakers, Dr. Bokhao and Rosenberg have given a very broad view on energy and hydropower. I will give a presentation which are very specific on eco-environmental impact and some adaptive management. So I would like to give my talk in 4 parts: research background. So as the previous speaker indicated, hydropower plays an important role in energy security and also the energy structure, in particular in China. The country promised in Paris Forum Summit that we will have a carbon peaking in 2030 and carbon neutrality in 2060. And hydropower plays an important role in this achievement, because in China we have the largest potential of hydropower reserve. However, the development ratio is about 24%. So we still have a lot of reserve to be developed. Also, we have going to build a lot of small hydropower and pumping storage. However, the river damming will make great impacts on river ecosystem, because they change the hydrological alteration and then the water temperature regime, also the biogeochemistry, cycling of nitrogen, phosphorus, and so on, and also the morphological dynamics, which will thereby affect the fish species and also the greenhouse gas emission. For instance, after the impoundment of the Three Gorges Reservoir in 2002, we see the dashed line. So in 2003, the spawning and fish catch declined sharply, which is about 24% of the previous amount. Also, they will have a greenhouse emission of carbon oxide, methane, and nitrogen oxide. So I will give my talk focusing on two research areas. One is the Upper Yangtze River. We have 4 dams in Cascade, and also the other one is in the Upper Mekong River, which have more than 11 dams. But I will study 5 of them. So in China, actually the eco-environmental impact has been studied for a long time. Why we continue this work? Because in China, we like to build high dams. We have dams more than 300 meters in height. So the impact are somehow different from the others around the world. So now I would like to give some information about our recent research on impact on biogeochemical cycles. So where's the knowledge gap? For instance, in the publication from Taylor Mafra in Yale. So she reported that the retention of nitrogen and phosphorus will increase with the water in recent time. However, in the Mekong River Commission report, before and after the impoundment of the Cascade reservoirs, the bioavailable phosphorus increase with time. Of course, urbanization and the population increase will have more input of the nutrients. However, the point is not only the amount is increasing, but also the species of the nutrients composition are different from upstream to downstream along the reservoirs. So the question is, what happened to the trapped biogeochemical elements in the reservoir, and what's the spatial pattern of the greenhouse emission in these reservoirs? So we did a lot of sampling along the reservoir for a number of years. We found that after river damming, although the total nitrogen and phosphorus don't have much change, however, the composition changed a lot. From the upstream to downstream, the phosphate increased, but the total nitrogen kept stable. Also, from upstream to downstream, we found that the total nitrogen is almost stable. However, if we look at this figure, we found that the ammonia increased and the nitrate decreased. And then we look at the composition of the minerals, we found the calcium decreased, but the ferric, the iron increased. So we proposed a kind of conceptual mechanism, which after river damming, the water will become stagnant somehow, and then this stimulate the growth of the algae, which absorbed the nitrate and also the dissolved phosphorus. And then after the death of the algae, they will sink down. Because in the deep reservoir, there's an anoxic layer, and then due to the reduction, we will have the decay of the organics, which will produce ammonia, and also due to the reduction environment, we will have the release of the phosphorus, which is the reason stimulate or increase the delivery of bioavailable nitrogen and phosphorus downstream. But this is only one reservoir. We make a model to calculate the Cascade reservoir. We reached the similar result that interception, that Cascade reservoirs will intercept the total nitrogen and total phosphorus. But there is an increase of bioavailable nitrogen and increase. And related with regards to the greenhouse emission, we also look at the Cascade reservoirs from upstream to downstream along the Upper Mekong River. We found in the reservoirs, the emission rate is far below the average worldwide. In particular, the emission rate decreased with the reservoir age, which is very interesting because in many reservoirs they will increase, but why in Upper Mekong River decrease? Because it has very narrow watershed and the input is small. The emissions mainly come from the origin deposit of organics. Also, look at the nitrogen oxide. The average value is also far lower than the global average one. But the importance is from upstream to downstream, there is a slight increase of the nitrogen oxide. However, this increase is not caused by the reservoir, but caused by the increase of the temperature and the increase of the input of nitrogen. That's the reason. Actually, reservoir doesn't make much contribution to the increase of the nitrogen oxide. So we made a special pattern of greenhouse gas emission in reservoir cascade, and we found that in the upstream reservoir, in the top upstream reservoir, it will be better to build a bigger one which can intercept most of the organics from the catchment, and then because it's a deep reservoir, we can reduce the increase the emission of the greenhouse gas emission. That's our research result for the future planning of hydropower reservoirs. The second part is about the fish conservation in river damming. So this is in China, we have the large reservoirs, and because of the high depths, we have a stratification in the reservoir, and then in summer period, we have the cold water. In the winter period, we have the warm water, and this will change the water temperature regime downstream and affect the fish spawning. Also, in the reservoir section, is a very high rapid flow or lentic condition, but after impoundment, it becomes a lentic condition. So the fish which spawns the drifting eggs, could they have a habitat for reproduction? That's the question. So the question is the physiological possibility of reservoir ecological operation for downstream. And the other one is, if we build a fish passage and move the fish to the upstream, can they survive, or they can find a proper habitat for reproduction? That's the question. So we first did the flume experiment in laboratory to test the required velocity and the increasement of velocity for the fish reproduction. And we found a very interesting one, that for the Chinese forecams, which are very, very important commercial fish for our food security. So we found that a pulse of high velocity for the spawning and a low velocity for hatching is very important. So for each year, at the end of May and to June, we need to increase our discharge from 12,000 and then for 4.5 days until 18,000. And then we need to trigger or to stimulate the spawning of the fish. And then we need to reduce the discharge to make the velocity to decrease. And then the eggs can fertilize and then hatch. That's very important. After the experiment from 2011, we can find a very sharp increase of the juveniles. If we look at the figure at the bottom, we can see after 2001, we have an increase of the fish eggs and also the juvenile year by year. Until 2019, we can find it almost reached the level before the impoundment. The other important finding is the time match of the accumulated water temperature and the critical temperature to stimulate the spawning. What does it mean? Which means the fish spawning need a kind of gonad development. So in the winter, when the warm water is released, the gonad development faster. However, in the next year, in spring, there's a cold water released. So when the mature eggs need to release, however, the critical temperature is not reaching to the required level. So there is a mismatch between the two temperatures. So we need to operate the reservoir to release cold water in winter and then to release warm water in spring to match the time and stimulate the fish spawning. after the experiment, we found that the fish has spawning activity was increased sharply. Then we needed to develop an optimized model for the discharge and also temperature operation, which means we have the objective function for hydropower production, and we have E flow, which is ecological flow demand, and also water temperature regime demand. And then the other constraint is the navigation. And then we build our model. We use the numeric method to solve the model, and then we get the solutions, particular non-inferior solutions, and then we can find a proper one. So after we get the optimal one, we can know the discharge curve and also the temperature curve for the downstream fish spawning. However, for the upstream, as I said at the beginning, for the river reach changed from the lotic one to the lentic one. So if the dam is more than 200 meters high, it's very actually irrational to move the fish from downstream to upstream. So how to protect the fish species in upstream? The way is to find a tributary for the habitat compensation. So the first one is we need to identify which tributary is the proper one and which is the target fish. So we use environmental DNA to do the analysis and the survey, and then we can find which tributary. For instance, there are a number of tributaries, and this is the main stream. So we need to find which tributary is the proper one for what type of fish, and then we have to do the survey, the habitat preference of the fish. For instance, the preference to the depth, sediment, and velocity, and then we build up a kind of habitat model, and then we can use our model to simulate the habitat suitability for different tributaries. And if the stream is not good enough, we can do some engineering. We can do some engineering work to improve it. For instance, remove some small barrier or dams to improve the connectivity, because if the fish spawn in the tributary, they need a sufficient distance for the drifting eggs to develop to juvenile. So we need to remove some barrier. This is a simulation result of the habitat suitability for the target fish. And this result shows before and after the removal of the dam in the tributary, and the increase of the fish. We can see after remove one dam, the fish increased from the downstream to upstream, which means the fish moved from the estuary, the confluence of the tributary, to the upstream of the tributary for the spawning and rearing. So this is mostly my talk today. So I would like to say the reservoirs can intercept the total phosphorus and nitrogen, but they can modify the nutrient bioavailability downstream due to the biogeochemical process in reservoirs, particularly in deep reservoirs. The other one is the reservoir in the upper Mekong River has very low greenhouse gas emissions, and the river damming doesn't increase the greenhouse gas emission. The ecological flow can improve the fish spawning, however, it's not enough. Mostly, it's important to operate reservoir for the ecological flow and the water temperature simultaneously. And finally, tributary can provide a kind of alternative habitat for the impoundment mainstream. So in future, we will focus on the other two elements in the hydropower development and ecosystem protection. One is the climate change, because the climate change will alter our inflow and also the temperature regime. The other one is using more advanced information technology, for instance, the DNA meta coding, and also some other model simulations. to improve our understanding and conservation measures for the diamond wafers. So thank you very much.
All right. So, thank you, Dr. Chen, and it's a great talk on the impact of river damming on the river ecosystem. And I saw Suresh. Do you have something to say, Suresh?
Only question I had for Dr. Chen, have the operators of these reservoirs, are they interested in these kinds of simulation approaches to actually make them operational in order to enhance the ecosystem of the rivers?
Yes, very good question. In fact, for some reservoirs, the ecological operation will somehow sacrifice the benefit of hydropower production. However, in China, we have a very strict law to force them to implement such kind of operations. In my slide, I'm not sure if I can show it again. Maybe
this. I want to interrupt.
No.
Maybe we are going to have.
For instance, we can use that
later.
they build up a kind of stop log gate. So it's very complicated stop log gates in the big reservoirs. So these are all built by the.
So Dr. Chen,
hydropower pump station.
Dr. Chen,
Yes.
could you hold your answer until after we speak from Dr. Hansen? We're going to have a Q&A period at the
Okay,
end.
sorry.
And I see
All right.
AWI's hand up. So if we can hold your questions, but please do post them in chat. We're collecting those.
All
So
right,
Dr. All right. Thank you very much. Go ahead.
Okay. So, yeah, I think very exciting talk. And so we are moving to the final talk by Dr. Carly Hansen. Dr. Carly Hansen works at the Oak Ridge National Lab, and she is going to talk about another aspect of hydropower, the footprint on greenhouse gas footprint of hydropower reservoirs. So, Dr. Hansen, it's your platform for 20 minutes. Yeah.
Great. Thank you so much. I'll switch over to my screen here. See if I can get that presenting. All right. Let's see. Am I in the?
You're good to go, Dr.
All right. Excellent. Thank you. Yeah, so I'm happy to talk about some of the challenges associated with greenhouse gas footprinting and modeling of greenhouse gases in reservoirs, and especially in hydropower reservoirs. So there's a lot of momentum to address greenhouse gases, and it's important that we are accurate in our accounting of where emissions are coming from, so that we can actually see if we're meeting emissions reduction targets, so we know what actions or processes are producing emissions, where we might be able to change course and even possibly mitigate those emissions. And the idea of a greenhouse gas footprint, or assigning an amount of emissions attributed to an activity or some entity like a reservoir, it's really helpful for vocabulary. But before we just take this idea off the shelf and use it, I think it's important to understand where there might be challenges or things to consider when we're talking about greenhouse gas footprints of reservoirs. So the first challenge that I wanted to talk about was it involves the foundational understanding of greenhouse gases and emissions. While it's improving, it's currently limited. So a recent paper on global methane emissions from all aquatic ecosystems, not just lakes and reservoirs, compiled measurements, and you can see for lakes and reservoirs just how sparse these measurements are. throughout the world. The emissions vary over several orders of magnitude, and again, this is just from relatively few sites. Methane and carbon dioxide can reach the atmosphere through several pathways, bubbling up through or ebullition in shallower parts of a water body. There's degassing that can occur when you have a sudden pressure change, and really methane-rich water from deeper in a reservoir passes through a turbine. And there's also diffusion of methane and carbon dioxide. So again, looking at these measurements, this is from a different database that was compiled by the International Hydropower Association. Folks there have developed a tool called GRES, which is aimed at helping people develop greenhouse gas footprints. So it really facilitates getting the information and putting it all together, information about land use, reservoir characteristics, the local climate, and water quality conditions, and helps calculate an estimate of the greenhouse gas emissions of pre and post impoundment. But underlying this tool is a database of reservoir measurements. And again, just like the methane specific measurements that I showed earlier, again, these measurements are still pretty sparse. So you can see these different pathways of ebullition, degassing, diffusion, and carbon dioxide diffusion. There's little clusters throughout the world, but again, pretty sparse, and that represents, you know, relatively few water bodies. Another way of looking at this limitation of the this underlying information and the measurements of greenhouse gases is by seeing, you know, different types of coverage that these measurements provide. So on the left, you see the actual values, the fluxes that have been measured, and then there's different periods that have been used for sampling. So some that represent only portions of the year, and again, that really varies by the pathway of emissions. So you know, many reservoirs were only sampled for a portion. Some represent annual conditions, and others just for the ice-free period. And in other words, the measurements are not consistent. On the right, you can see a breakdown of emissions measurements for just the US, and just another way of looking at this, comparing the different time frames over which these measurements were taken, and that varies regionally too. So again, you see a lot of inconsistency, and the big takeaway with this is that it kind of weakens the confidence and robustness of any empirical relationships. So statistical models that estimate emissions based on factors like size or age or local climate aren't as strong when you have this variability in the observations that are being used to develop those empirical relationships. And ultimately, this also means that we have less data for validating process-based models of greenhouse gas emissions. So this limitation in measurements really is a difficult thing for modeling, and can be a significant challenge. But the next challenge that I want to highlight is that the water bodies themselves are not constant. So to illustrate this point, you can see a water occurrence map of, this is Douglas Reservoir in East Tennessee. So the lighter pink and purple shades show where there's not always water present or detected by satellite imagery. And the blue is where you consistently see water detected over this satellite record. This variability in where water is, or the size of a reservoir, really contributes to some issues with uncertainty and scaling up whenever you're dealing with aerial fluxes, or averaging an observation over the area of a reservoir. If that area itself is changing, that obviously create some pretty foundational issues. Many studies report the emissions as total emissions per unit area. So that can be pretty problematic if that water body size is changing. Additionally, if water body size is the predictor for emissions, as it sometimes is used, especially in some of these smaller coves and at the river reservoir interface, you see a lot of variability in the surface extent there. And that's really important for, especially for methane ebullition. So in this figure, you see the bubbling and ebullition concentrated in these shallower zones. So if you have a lot of fluctuation happening there, that can create a problem for your measurements, but also when then relating that or developing relationships and empirical models. Another way to think about variability of water bodies is that the volume and the depth is changing, not just the extent. And that varies throughout the year and from year to year. So on top, this is the normal operating range for Douglas Reservoir. So storage or volume of water in million cubic meters. And that varies throughout the year and from year to year. So there's a range. And between that upper and lower bound on this normal operating range, it's about 600 million cubic meters, which is about a third of the total capacity of this reservoir. So it's a significant amount. So I just want to emphasize that. But Douglas Lake is not unusual. When you look at the large reservoirs in the US, these are all of the, or most of the reservoirs from the GRAND database that are in the US. And if you look at that range between the upper and lower bound of operating range or operating storage, the median for both the non-hydropower and hydropower reservoirs is about a third of the total reservoir capacity. So again, just a lot of significant fluctuation. And that makes it really important, to consider what's actually happening, what's in the reservoir when measurements are taken, and to take into account that there could be big changes in volume over the life of the reservoir, and that volume and depth fluctuation should probably be taken into account or modeled, especially if looking at emissions over time. But the water bodies aren't the only thing changing, and the surrounding area is changing as well. So this example is a reservoir in Iowa. This is the Red Rock Dam near Des Moines. And it's in a heavily agricultural area, and Des Moines is a pretty big city with lots of development. You can see the changes in land use over time, and that really could have an impact when you have different activities and watershed management strategies that might be changing. So that could result in differences in nutrient loading, the wastewater inputs to a reservoir. And additionally, this is a big topic with the growing issue of wildfires and drought impacts on land cover and hydrology, especially in the Western US. It can really drastically change the carbon nutrient input and the hydrology, which could very much alter water body emissions and driving processes in the reservoir. So lots of changes nearby that could have big impacts. And the last aspect of change that I want to highlight is the local climate. In this map, you can see for the United States how climate classes are projected to change from the recent past to the end of the century. So in the example that's highlighted, there's a hydropower reservoir, hydropower and water supply reservoir in north central Utah, Jordanelle Reservoir. The watershed is not heavily developed, but that watershed happens to be located in an area that's that's projected to have a really big shift in climate. And there's increasing temperatures as it shifts from warm to temperate dry. There's shifts in the timing of precipitation. So, you know, what that means for the reservoir and the greenhouse gas emissions is, you know, impacting thermal stratification, impacting local hydrology, and that has a lot of possible follow-on effects, which could really change how carbon's processed in the reservoir, and the other associated you know, driving factors or driving processes like eutrophication, and so lots of follow-on effects that could contribute to and impact greenhouse gas emissions. And there's a few other considerations that I want to highlight, in addition to the measurements limitation and the just different types of changes that are possible that could impact emissions. The first is that water body data sets can be really inconsistent. This is really relevant for large scale modeling, which often relies on GIS data sets that are really large scale. But it's really important to acknowledge that these data sets don't always talk about water bodies in a consistent way. So to illustrate this, there's the Grand Coulee Dam, which is one of the biggest, it's the biggest hydropower generator in the US. But the impoundment behind the dam, which is known as Lake Roosevelt, does not exist in some water body data sets. In some data sets, it's classified as a lake instead of an impounded reservoir. Sometimes it is classified as a reservoir, and sometimes it's classified as a stream or a river. So that could really change especially as you increase the scale of modeling or talking about emissions with respect to different sources and assigning those to the source of an aquatic ecosystem. If the water bodies aren't consistently described, then you could end up with some inconsistencies just because of which underlying data set you're using. I also want to point out that the characteristics that are associated with these water bodies are often pretty variable. So even really simple things like surface area and storage can vary a lot depending on which data set is describing that water body. Another point on this, it's really critical that we understand which water bodies are rivers and which are lakes or reservoirs, because certain relationships that are represented, like the processes driving ebullition or diffusion in a river, those same processes and relationships may not hold for lakes and reservoirs. So it can make it really tricky if some relationships don't actually apply. So some impoundments actually have really minimal storage and look or act more like a river than a reservoir. And you know, the measurements from the global methane study that I showed at the very beginning shows there's quite a bit of differences in the methane measurements at rivers versus those in more lentic systems. So it's an important delineation, but one that's not as straightforward maybe or as consistent as you might think. Another challenge that is tied to water body data is that reservoirs and managed water bodies don't exist in isolation. We saw a good example of this with the research areas that Professor Chen talked about was a cascading system of reservoirs. And when you have these links between reservoirs, there's a lot of connections and coordination. And these are sometimes viewed as complexes of facilities that have to coordinate operations for specific purposes. This example right here in this map is more than a dozen reservoirs in the ACF basin in the Southeast US. And they're operated for flood control and water supply. And there's a really big range in their size and the conditions, even though they're on the same river network. And again, there's a lot of coordination in operations. So it can be actually kind of difficult to cleanly delineate where one reservoir's footprint is, especially when the operations are so tied to other reservoirs. So just an important consideration, and that reservoirs are so often connected to either each other or other water bodies. They don't exist in isolation. And related to that, there's challenges with attribution of emissions and how we talk about them, either the intensity of emissions or a footprint with respect to generation or a footprint with respect to area. And this graphic on the right really shows it shows how footprints look if you talk about per unit energy on the y-axis and per area on the x-axis. And I want to call out a couple of reservoirs that illustrate this kind of tricky situation. So reservoir A that's labeled is a small dam, small older facility that had generation added after the fact. It was a mechanical plant before it was producing electricity. And it's in an urban setting, and so very different conditions compared to the reservoir that's labeled C, even though they're similar in size and volume. These two impoundments have extremely different footprints, and that's largely due to the relative size of how much generation was able to it was possible at that facility relative to its size, the surface area and volume size. So in contrast to that, you see a really big reservoir that has a really big footprint here. This is the Sam Rayburn Reservoir in Texas. It's very large, and it is a hydropower, or is used for hydropower, but there are other purposes that determine its operation, so flood control and water supply as well. And this reservoir has a history of really high nutrients and issues with low dissolved oxygen. So there's some aspect of the watershed and reservoir management, and those strategies contributing or even driving some issues with emissions that may not be directly related to the actual hydropower activity. So again, it's this extra layers, some extra baggage that is associated with these reservoirs and their emissions that may just require some additional explanation beyond just looking at the footprints, whether it's a footprint with respect to generation or with respect to area. And the final point on attribution and what makes this so challenging, even when you have an activity that's pretty directly linked to hydropower, so the pathway for emissions of degassing, where you have methane-rich water from low in the reservoir going through a deep intake and then going through this big pressure change, you might think degassing wouldn't occur if you didn't have that arrangement. Degassing might also not occur if you didn't have really methane-rich water, or if the water quality did not support those conditions, or if the reservoir characteristics itself weren't supporting other operations. So again, there's just a little bit more to the story that I think is important to take into account. So of course, I just spent a lot of time talking about the challenges, but there's some light at the end of the tunnel. So satellite imagery can really help get a lot of information about how things are changing over the past and even on a near real-time basis. There are a lot of efforts for large-scale monitoring and increasing our coverage of observational data. And to go along with that, there's also a lot of remote sensing that can support that. Satellites and aerial imagery from, or aerial measurements from the GHG-SAT instrument, for example. And there's a lot of high frequency monitoring networks that are being established and could be really powerful for understanding coincident conditions that could be affecting emissions. And finally, there's a lot of progress that's being made in this water management, infrastructure, hydrology, and water quality data worlds, bringing together all of that information so that we're better able to look at water bodies and reservoirs and their emissions on large scales. And I just want to end by acknowledging the rest of my team, the principal investigator, Natalie, and the team of people working with me at Oak Ridge National Lab, as well as the folks at the International Hydropower Association who have been developing the GRES tool. So thank you so much.
Okay, thank you very much. So we have 4 very exciting talks, and so without, I think we already kind of behind schedule. So we are going to move to the Q&A question session, and Christina, you are going to maybe start chairing this session, moderate this session, and I'm probably working with you maybe to read some of the questions. Right.
Okay, perfect. Thank you all for such amazing and informative presentations. Really appreciate your time today. So to kick off the Q&A, and please continue to add questions in the chat if you have any questions, I'll go ahead and ask them. The first question was to Dr. Bockenhauer. You replied a little bit in the chat that said you're happy to expand more in the Q&A, but it was in regards to, is there any coordination between Hydrowire and other renewable energy programs, i.e. solar and wind? So maybe for the benefit of the larger group, you can just respond to that and expand if needed.
Yeah, and it's a good question. And so at DOE, you know, we're a research organization and we do many other things, and we're the energy ministry for the US basically. And so the way that we're organized is that there's a hydropower and marine energy office, which I sit in. There's a solar office, there's a wind office, there's, you know, fossil fuel offices. There's lots of different types of offices that are each standalone, but as you've heard, you know, from my talk and from others, it's of course really important to think about the entire power system when you're thinking about the future and how we're going to get to a decarbonized system. And so that doesn't lend itself well to a siloed approach where you're only thinking about single technologies. So we recognize that. We've done a lot more, even just in the last 5 years, I would say, on coordinating between offices. We've got initiatives that are DOE-wide that relate to energy storage, so that work on pump storage as well as batteries, as well as flow batteries and other types of hydrogen and other types of storage technologies. And we've got grid initiatives where we're working on transmission together with solar and wind deployment and you know, different technologies like that. So we do recognize the need to coordinate, and we do that. We have close relationships with researchers in other offices. I'd add too that our national labs, like Carly works at Oak Ridge National Lab, and there are other DOE national labs across the US. A lot of the researchers there will work some of their time on solar and some of their time on transmission and some of their time on hydropower. So, you know, that perspective is kind of embodied in the national labs as well. So I think we do that coordination, but we could always do more.
Wonderful, thank you.
So I'm going to read the next question. I don't know who raised this question to Dr. Chen. Can we customize your research to our region? I think this is probably somebody who is not from China, and would ask you if your research can be customized to other regions, maybe like in Middle East or in South America?
I think mostly we can, because the technologies and the approach are similar, but we need to do a lot of field sampling to collect the data, and then we can do the analysis and calibrate the model. Yeah.
All right. I think probably that's good answer. All right.
Perfect.
Yeah.
So moving on to the next question, to Dr. Rydlbach, can you give us a projection of future hydropower? Oh, that was answered live. Okay.
Okay.
No, Christina, I'm sorry. I typed it too fast. He hasn't answered that yet.
Okay, I didn't think so. And then I was
All right. Okay.
No, I'll stop typing so fast.
All right.
We have a Google Doc where we're behind the scenes working on questions. So now you have a window into our method here. But the question is, can you please give us a projection of how future hydropower technology that can be totally revolutionary compared to today's technology?
Totally revolutionary, right? What
Yes.
does it mean really? So it's a good
Pie in the
question
sky,
anyway.
big
Huh?
picture.
This is a good question. I mean, we have to say here that hydropower is around for, let's say, roughly 100 years, right? So if we compare this to cars, which we all used to drive today, cars are around also for about 100 years, more or less. So they still have 4 wheels. And what is a big change on cars, let's say, just starting with this example. So the big change is really, it may be more convenient, a better suspension, larger engines, gradually improving and developing to higher technology level. And I would say that for hydropower, it's, let's say, in a very similar way. Because in cars, again, you have fancy navigation systems, like maybe self-driving if you dare to do this. And for hydropower, it's also gradual development. So what I was trying to say is this part on the research, that the use of extensive numerical simulation will really put a chance and will improve geometry to better suit let's say, new operational requirements. So like, and I skipped this part, but we have a framework, a system, design system framework, which may automatically optimize for flow and also strength and stress. So we can have both limits. And so that means we can come up with a geometry which is the same time is good for flow and good for stress as well. Then, like what I was saying or trying to say with predictive damage assessment under this general topic, we are working on, let's say, methods to better predict necessary maintenance, because utilities typically want to have maintenance-free equipment as long as possible, say, to just generate to sell electricity. And this is part, and then also better diagnosis for machine during operation. I mean, I showed this little, let's say, pump unit, which is really used to very simple acquire data, because if you always go to large plants, it's very difficult to acquire data. We have only few data, like what we just have seen in the last presentation. It takes a lot of time. So the method development is really done, let's say, with more simple type equipment, and then can be transferred to large equipment. And the last thing maybe is, you know, the physical rules still hold. So like a wizard type style of machine is kind of difficult. So because we have still mass balance, energy balance, angular momentum balance, all that, which governs really the function of the machine. And so we can look into how can we convert potential energy, how can we convert kinetic energy. And so there's different ways of doing this. But to what I know, like if you use just for these propeller machines, they have theoretical limit of a little less than 60% efficiency. If you use like diffusers and shrouded propellers, you can shrink the size and still get more power out of it. So this is, I can't show this yet. So in half a year, I could show this, what kind of geometry we developed with this overall optimization method, which is a significant power increase towards what you typically do manually. So in this sense, okay, it gives at least some ideas, but I believe, you know, we are engineering, say, we are mechanical engineering, electric engineering. This is gradual development. We are not physicists who may come up with some new small particles which do something which we don't understand yet. So I hope this helps for.
All right. All right. Okay. All right. Okay. Thank you. I think it's a great answer to the question. And so I'm going to ask the next question to Dr. Chen, maybe also Dr. Hansen, is you know, what when you talk about greenhouse gas emission, you know, from hydropower plants, but also there is a reduction in greenhouse gases because of the replacement of the fossil fuel power. So can you maybe give us a ratio of, you know, the emission and the reduction of greenhouse gases of the hydropower plant?
Let's see, will you take it first?
I think either one of you, I think maybe Dr. Chen answer first, and maybe Kali, you can also answer this question. Is the ratio between the you know, you have emission from the reservoir, and then you have reduction because of replacement of the fossil fuel. So what's the ratio between them? What's the net benefit?
It's a good question, but also it's a very difficult question to answer. Because first, I don't have the number in my mind. Second, it depends, because in some countries or in some reservoirs, the emission is high. But for instance, in the reservoir in Brazil, they inundated a lot of forest, and they have a long time and high emission. But in some reservoirs, for instance, in the Upper Mekong River and also in the Upper Yangtze River, we have very low emission because we clean all the things before the storage, you know. So they have very low emission. So it very much depends, but I can give a number. So in 2010, we have the core for the energy is about 75%. But in 2021, I mean, after almost 10 years, so due to the hydropower development, so we have the energy from coal for 60%. So we have a reduction of 15% of the use of the coal for energy. That would be a number. Yeah.
Okay. Connie, do you want to also, you know, address this question?
Probably just to echo what was said, I think I shared the observations span a huge range. So post-impoundment emissions are really variable and very reservoir specific. So and then I'm so glad that that it was brought up, the treatment or kind of the pre-impoundment conditions are also really huge. So yeah, I don't think I have anything to add besides just, those 2 points are really really nailed it.
Perfect. Well, I think we'll finish up with one last question before we close. Also to Dr. Hansen from Charus. Can you tell us a little bit more about the monitoring instrumentation and how expensive the setup is for an average reservoir?
you may guess, I may quickly jump to the fact that it's difficult to have an average reservoir, but so I'll say for each pathway, there are different instruments required. So that's an important thing to account for, that measuring all of those different ways that the emissions are reaching the atmosphere requires different instrumentation or analysis. It's not just one instrument, but I think we're on the order of tens of thousands of dollars per instrument. So depending on the size, multiple instruments may be required, but likely personnel is going to be the largest cost of any kind of high frequency monitoring. So once the instrumentation is in place, there's still the maintenance and the analysis of samples that requires the people aspect of it, and that's usually the highest part of any type of sampling campaign like that.
Wonderful, thank you. With that, I think we'll close out the Q&A session and turn it back to, I'm not sure who's closing the session today, Glenda or Sarush.
I'll do that. Again, I'd like to thank you all, the speakers. It was a wonderful kickoff of our 2022 Thinking of Academic Year 2023 Rosenberg webinars. I wish you all happy holidays. Our next one will be on the economic and social impact of land subsidence, taking it from a global to local assessment scales. And that will be on Tuesday, 21st of February. I hope many of you will be able to join. And with that, on behalf of Glenda and myself, we thank you all, and especially the speakers.
All right.
Bye-bye.
Bye-bye.